So you can set up conditions in which a person is not prepared to say they saw something. You've reached the subjective threshold, but they're nonetheless influenced by the stimulus. That's kind of interesting, maybe practically interesting, as I say, in terms of advertising. But does it mean anything psychologically? I mean, it might just be the case there's perception, and then sometimes people believe they saw, sometimes people believe they didn't, but that's just how it is. That doesn't change. The perception is always just perception. There's nothing further to say about it, really. That's interesting. So what Merkel argued is if you could find qualitative differences between perception below and above subjective threshold, then we have theoretical work to do. Then that shows there's more to this than just saying, oh, people just have some bias for saying when they see something or not. That's the end of that story. We can just get on with analysing perception and talking about perception without being interested in whether it's subliminal or not. But if there's qualitative differences in perception above and below subjective threshold, then we need to understand, well, how is it different? How does it work when you do theoretical work? So here's a study that set out to show qualitative differences, to show, in other words, subjective threshold is theoretically interesting. It's a Stroop task again, but with only two words, red and green. The word red or the word green was displayed. A variable stimulus onset asynchrony, set to be either above or below that subject's individually determined subjective threshold. And then red or green colour. The task of the subject was to say what the colour of the ampersand here was. Now, the slightly unusual feature of this Stroop task was that there was a manipulation of the proportion of congruent trials, so that in one block 75% of the trials were incongruent. What that means is if you knew you were seeing the word red, you knew there was a high probability of green coming up next. You see, so you could predict the opposite to the word in principle. And in the other block, it was the other way around, 25% incongruent. Now, here's the results. Sub means sub-threshold, below the subjective threshold. Supra threshold, above the subjective threshold. Now, what happened for the incongruent trials, where we have this 75% incongruent trial block? Here's reaction time up here. Green is incongruent. Notice when you're above the subjective threshold, you're faster on the incongruent trials than the congruent trials. So why would you be faster on the incongruent trials? Yes, that's right. There's a high degree of predictability, and you know it's going to be the opposite to what was there. You can guess it. On the congruent trials, the unexpected thing happened, so you were slow. On the incongruent trials, you expected the opposite to what was there, but you expected it, so you could be fast. You see. So you got a reverse Stroop effect. So now, because this is above threshold, subjects would be consciously aware of consciously see the words. They could consciously notice the 75% relationship, and they could consciously use it as soon as they notice the relationship to make the predictions, and they could use that predictability to speed up their reaction time. So the question is then, what happens below the subjective threshold? We get the opposite pattern. In fact, we get the normal streak pattern, where you're slower to the incongruent trials than the congruent trials. As you might expect, you just get the automatic priming happening. The subjects don't make use of the probabilistic information. They don't make predictions. So it's something that you could do with conscious knowledge. You can, even within a few trials, as soon as you notice it, you can make a connection between anything and anything else, and you can use it immediately to control performance completely if you want. More or less limitations, but as in this case. So one way that's been put is inferentially promiscuous. When you have conscious information, you can put it together any way you please, use it any way you please. But the unconscious information, can you use it any way you please? No. So that seems to be an interesting difference between the two. Now that's not to say, just to update you from that, because that was an early study, that's not to say, you can say, well, why couldn't you sort of gradually come to unconsciously learn to use the information that was there? And indeed in more recent studies, and I give this one here, 2015, Consciousness and Cognition, they show you can learn potentially gradually to make use of the probabilistic information, and so the Stroop effect begins to shrink with this proportion of congruency information. But it's relatively small. It takes time. And in this more sort of recent replication here, when you compare that with conscious-unconscious, you get a bigger effect when things are above the subjective threshold. So this dissociation still conceptually holds with these more recent sort of tweaks. Now look at another study carried out in Sussex, looking at the extent to which unconscious perception could be involved in some sort of strategic control. See, what we have here in this study is a large degree of strategic control that wasn't shown unconsciously. And as I said, that doesn't mean that unconscious information couldn't be used to engage in strategic control at all. So let's just have a look at that. Although, I'll just say at the beginning, and we'll return to that, according to Jacobi, strategic control is what consciousness does. So what we're about to do is put Jacobi in conflict with the subjective threshold. How we'll do that? Well, let's say you gave subjects instructions to pick a word, like you say, pick dog. That's instruction. So then if the word dog and cat came up, they'll press the button for the dog word. Or you could have the instruction, not dog. Let's say that was your instruction, not dog. Dog and cat comes up, you've got to press the button for cat. Now what would happen if you gave these instructions subliminally? So you flash them up, backmask them, so that they're below the subjective threshold. So this is what we did in a series of experiments. We also call the subjective threshold, by the way, the guessing criterion. We'll come back to that when we talk about implicit learning, because you take the trials of the person says, on a trial-by-trial basis, I'm completely guessing about what was there. So those are the trials of which the person is below the subjective threshold, on a trial-by-trial basis. So this is what Anna Marie Armstrong found, who's a PhD student here. when you tell people to pick a certain word subliminally, and then you present them with two words, they say they didn't see what the instruction was. You say, that's fine, just guess which of the two words is the one you should be, you were guided to pick. They're picking about 60% correct, the one they're asked to pick when they're told, pick dog. Pick whatever the thing is. Well, that's not too surprising. You would imagine that familiarity priming would guide you to the word that's just been displayed. The question is, if you had not dog, can you unconsciously take on board the word not, subliminally presented, in order not to pick dog? Because the word dog that's just been presented would be priming you to pick dog, right? So you might think, if you're given, and a Jacobi take on this would be, if you're given not dog subliminally, you would pick dog above chance. Because you're guided towards, you can't exclude it. You're guided towards dog. What we found was people followed the instruction in a series of experiments at above chance rates. So they could avoid, to a small degree, less than 60%, but nonetheless significantly above chance. They could exclude the word they'd been subliminally asked to exclude. So this is, so they're asked to exclude, I keep saying dog, of course there's a lot of words versus dog. They're asked to exclude dog. They're telling you they didn't see what the instruction was, they're purely guessing what the instruction was. So the instruction to pick or not pick was delivered, in that sense, subliminally by subjective threshold. So by the subjective threshold measure, they had processed the instruction unconsciously. Now, according to the process association procedure we're talking about, did they do this consciously or unconsciously? Have they successfully excluded? Yes. No, but but being strict about process association procedure, was it conscious? Yes. So there's conflict between the two criteria then. So why don't you just say to the person next to you, what do you think? Was this conscious or unconscious? So one way of looking at this is, for those who have this concept, is in your diary, unconscious control. By high order thought theory, so first theoretical principles as it were, we have a case of unconscious processing involving strategic control to a small degree. As I've written here, when you ask people to do it, when the words are conscious, they do it about 100% right. So we could still say a function of consciousness is possibly strategic control. Just because unconsciously you can do something a little bit, it doesn't mean that that's not the function of consciousness to do it really well. Right. So strategic control might be something that's associated with consciousness. It just doesn't define it. It might even be the function of it. So that's summarise that. That little bit is to say, relatively easy to get subliminal processing below subjective threshold, and there are arguments that the subjective threshold is something interesting, psychologically interesting. Now to return to the objective threshold, and argue there is some evidence you can get processing below an objective threshold. Maybe with backmasking it's particularly difficult, but with backmasking, remember, we had to flash things very quickly and interrupt processing with a mask after, say, 30 milliseconds or quicker. the subject to reach an objective threshold. With some of the new techniques, we'll look at two of them now, you can maintain information for longer. And so maybe that gives us a better chance to allow it to be processed in interesting ways, even while it's being maintained at an objective threshold. So here's an interesting study in which used continuous flash suppression. So in one eye you see this moving, colourful display, and the other eye you show images, including sometimes a naked image. What the subject consciously sees, because of all the movement and the colour and so on, is this sort of random, colourful, dynamic display. In fact, if you ask them which side was the human image on, left or right, they perform convincingly close to chance in objectively saying left or right. So it seems we've got pretty good evidence here for an objective threshold being used. Now the task the subject had was on either the left or the right of the display was this slightly tilted patch here, and the subject had to say was it tilted a bit to the left, tilted a bit to the right. Now the idea was that if your attention had been drawn to one side, to the left or the right, you would be faster or more accurate in indicating the tilt of the patch. And that's the attentional effect here, how much better you are at indicating the tilt of the patch. The attentional effect is whether you were drawn to the same side as the naked image or not. And what they found for heterosexual people was the attention was drawn, for both males and females, to the same side as a naked image of the opposite sex. Homosexual people, other way around. So the slightly disturbing thing about this is the subject need never know there was a naked body here at all, and yet their sexuality could be protested. Absence of knowledge that it does. In any case, what this showed was using highly biologically relevant stimuli, namely naked bodies, displayed for considerable periods of time. You see 800 milliseconds, longer than, say, the 30 milliseconds needed for backmasking. You could get priming above objective threshold. Here's another method of, which I mentioned last lecture, of displaying a stimulus for long periods of time, indefinitely, without the person being aware of what was there. So in this case, the person's looking at a cross. There's a face which is making an expression, surrounded by other faces, causing a crowding effect. So these faces around the prime here mask it and block it from consciousness. As long as you're looking at the cross, you don't see what that expression is in that middle face. This shows what happens in this gaze contingent crowding paradigm. As long as you're looking at the cross, the face is there. Because the eye movements are being monitored, as if the person tries to get a sneaky look, just can't help themselves, has a look at what was there, it's substituted for a neutral face. So you never get to see what the emotional expression was that's being subliminally presented to you. So you can show happy or angry faces here and maintain them at what's apparently an objective threshold in terms of the person being able to say what the emotional expression is. And then see how much people like what's to them an unfamiliar Chinese character. So they're rated as more or less pleasant because of the prime that they've been presented with. And indeed, there is this emotional or aesthetic priming effect, where for happy faces, the character is rated as more pleasant than neutral or angry faces. So again, we can get, with new methods, we can show somehow the information gets into the brain and influences you, even though you can't use that information to discriminate what's there. So the summary of that little section is, if the conditions are right, you can get perception below an objective threshold. It's much harder. Of course, it's not surprising, because if you degrade the stimulus so much that you can't discriminate what was there, based on the conditions of the experiment, it's not surprising. It's difficult to get that stimulus to have further effects on you, but it can be done. But if you really want to look at the power of subliminal processing, why not just go below the subjective threshold, where the stimulus is relatively well processed, and the person doesn't believe they saw it, and you can get good subliminal effects that way. So now I want to look at the question of whether we can use any of these methods we've been talking about to ask the question, how does the brain relate to conscious experience? Or how it's sometimes called, what are the neural correlates of consciousness? So that's one of the deep mysteries. Why would a brain give rise to conscious experience? How does it work? What about brain activity, function, gives us conscious experience? One way of looking at that, which we'll come to, is what's the difference between conscious and unconscious perception. So at the level of wetware, wetware just means hardware when it's a brain. So what about your hardware, this stuff here, makes the difference between conscious and unconscious perception? So we can understand what processes in the brain, correlated or maybe are or enable or explain conscious awareness. But if you're a higher order thought theorist, that would be what brain structures or processes correspond to higher order thoughts. How does that happen? If you're a global workspace person, it would be where in the brain or how in the brain do you implement a global workspace. So we're going to look at two strategies. One is to keep the stimulus, the external stimulus to the person the same, under conditions in which conscious perception is changing, namely that's binocular rivalry, right? Because then what you have is the same external conditions, but just changing conscious experience. So that seems a particularly useful way of looking at the correlates of conscious experience. So that's what we'll get to look at before the break. And then we'll look at the difference between conscious and unconscious perception. So what you have there is you have perception both times. At one time conscious, the other time unconscious. Maybe that can tell us something about the neural correlate of consciousness. So to remind you, binocular rivalry, you present one image to one eye and another image to another eye. Remember, this isn't something the brain is ever exposed to in everyday life. two eyes get extremely similar images. Slightly displaced, which you use for depth perception. But nature doesn't present a house to one eye and a face to the other in general. And what happens is you don't experience a house face, but you experience a face that then sort of crumbles, a house grows in the middle of it, and then there's a house, just a clear house, half a dozen seconds, and then that starts to break down, and then you have a clear face for 5 seconds or whatever, and you have this alternation. So what you're displaying to the subject the whole time is the same, though. Conscious experience is alternating. So what changes in the brain with the alternating conscious experience? Well, it turns out some visual areas stay pretty much the same, like V1, the first visual area. That respects a fair amount what's objectively there. But we see here some specific areas change. So we have the PPA, the parahippocampal place area, and the fusiform face area. And when the subject presses a button here to indicate it's just changed, it's switched to the other one, then we find these particular areas switching. So maybe that's not too surprising. Areas to do with face perception go up and down as the person experiences a face, doesn't experience a face, experiences a face, doesn't experience a face. And areas to do with location and places, doing that counterface for the houses. So there are sort of object specific, category specific areas in the brain that are switching back and forth. Now, one thing about neural correlates of consciousness that's slightly difficult. So, okay, but does that mean that these are the areas that are responsible for conscious awareness? Can't quite say that. They could be the areas that. So there's two possibilities. There could be the areas that feed into the conscious experience areas. They're earlier than it. So particular areas of the visual cortex that code particular objects and so on, well, temporal lobes that do that. It doesn't mean that they might be fluctuating, but they're fluctuating because they feed into the conscious experience areas later on. So they could either be a bit before or a bit after the areas we're interested in. So we need to look a bit more fully over the brain to see everywhere that's changing. This experiment had two images, binocular rivalry again. One stimulus was not one thing to one eye, one thing to the other eye. It was the images that were shown to each eye, but you saw half and half. So you just had a stable, this is a control condition, just a stable half a house, half a grating, sorry, half a face, half a grating. You just saw that constantly the whole time in the control condition. In the so that's this. You just see that constantly. That's the control, stable viewing. For this, the rivalry condition, you saw this one, then it flips to this one, then it flips to this one, and so on. So now what we have is two fairly similar conscious experiences in a way, but one of them is alternating and the other is stable. So the content otherwise is similar, but there are different conscious experiences. One is alternating, one is stable. They found the switch rate of the subjects, and then they didn't get the subjects to report when they switched, because they didn't want the confound of report. So you could say, if you find somewhere in the brain that lights up and people publicly reports it, you could say, well, that's the bit of the brain that's responsible for deciding to publicly report. report something. And that's different from conscious experience. So what we'll do is have the subject just sit there and look at this, because we can keep a track on things, because one of the images is stable and the other is switching about every 6 seconds. If we look in the brain, we can see what has the same temporal structure or flipping rate, what's changing around every 6 seconds. That's the one that's corresponding to the conscious experience, without the subject having to report anything. Do you get the logic of that? And what they found was that brain activity was correlated to this temporal structure all the way up into the frontal regions. So they argued that conscious experience could well depend on frontal activity. You know, it's fed into by visual areas, but then we still need evidence for this claim, but here's a hypothesis. It depends crucially on what's happening in frontal regions. And we're going to look at this claim. This isn't quite enough to demonstrate, as I said, because all we've shown is there is the right temporal structure sort of lower down in visual areas, and it goes all the way up to the frontal regions. But which part of that is relevant for conscious experience? Which bit precedes conscious experience? Which bit comes after conscious experience? So one hypothesis is frontal regions is important. Just hands up if you understand that experiment. Is that clear? Good. If you think it's a little bit unclear. So this notion of getting at the neural correlates of consciousness without people reporting has recently been developed a little bit more. So just tell you about one of the paradigms that looked at that to try and sort of finesse or make it more subtle. For example, what you can do, and this is what Frazel et al. Did, is present to one eye a grating moving one way, to the other eye grating moving another way. Now, why you do that is because when you consciously see a grating one way, your eye has a characteristic pattern of eye movements that tracks that grating in that direction, optical nystagmus. That means you can tell by looking at the eye movements which way is the person seeing the grating. And that's kind of interesting, because then you don't need a report from the person. You don't need to get them to tell you what they're seeing. You just look at their eyes and say, yeah, they must be seeing it moving that way. Or another way of doing it is having a relatively bright patch to one eye, dark patch to the other eye, and you find pupil dilation matching what they're consciously seeing. So again, you don't need to get the person to tell you what they're seeing as it switches. You just look at the eye, pupil size, and you say, okay, they're seeing that. So as I say here, you can do away with public report, the person having to decide when to report, and you just use these indirect measures to know when the switches happen. So that's quite a neat idea. The methodology they happen to use in this experiment is something called switching versus replay, which is what they do is there's a switching condition where you have one thing to one eye, one thing to the other eye, so that's the binocular rival we've been talking about. But then to control everything and make it as same as possible, what you do is you play a sequence that's the same. First movement that way, 6 seconds, now movement that way, 6 seconds, now movement that way, 6 seconds. And so that's what you see. The trouble with that for looking at neurocorrelates of consciousness is the person's having the same conscious experience. So when you contrast switching versus replay, you're not really looking at the neurocorrelates of consciousness anymore. So unfortunately, that means this study doesn't tell us anything about the neurocorrelates of consciousness. But what they did find when they compare these two conditions in report versus the no report condition, that you get more frontal activation when people publicly report, which shows it does make a difference. That's the main sort of methodological moral of this. When you ask people to report, just to press a button, you say report, it's just pressing a button, you think that's simple. Actually, the frontal lobe lights up rather noticeably more just in the act of pressing a button. So that does show that that is an important consideration. But the results don't show, even though some people have tried to say so afterwards, that they don't show that the frontal lobes are not involved with conscious experience. All this study shows is they're involved with report. Something short and taken into account. Remember, we have this previous study here, which was no report, and in a genuine comparison of two different conscious experiences, we get the frontal lobes involved. So my conclusion is that the frontal regions are involved in some way with conscious experience, and the more recent talk of no report paradigms in no way undermines that claim. Of course, we can still ask, after the break, we're going to consider, maybe the frontal regions come after the generation of consciousness, or maybe they're involved in generation of consciousness. We don't know that. I'm going to attempt an answer to that later. I'll just say at this point, as I was saying to you earlier, if you read Daniel Dennett, he'll say there is no answer to that, because it's just however you want to talk about it. And if you're interested in reading that further, Daniel Dennett's a very good read. Nonetheless, I'm going to attempt to give you an answer later. But let's first break for coffee and meet back here in 10 minutes. Now I want to turn to the second strategy for looking at how the brain is involved and might explain conscious experience. And that's to compare conscious versus unconscious perception of the same stimulus. This classic study, Dehaene, presented a word at objective threshold, or clearly visible, and you just do fMRI scan and see what happens. And his argument was that masked words, when they're subliminal, activate particular local areas of the brain. So a word would activate word processing areas, face areas, and so on. But when the word becomes visible here, you see large-scale activation across the frontal parietal network. So, one conclusion from this, which is Dehaene likes the global workspace theory. He's developed a particular version of that himself, and a computational model of it, is conscious awareness just is information being widely available in the global workspace. When the information is widely available to be used by anything, then that's conscious. Or it could be, it's being widely available isn't what made it conscious. Maybe it was, because it was widely available, it reached a particular area, maybe an area responsible for creating higher order thoughts. And that's the important thing. So the data don't distinguish the two main theories that we've been talking about, higher order thought theory from global workspace theory. What Hakwen Lau argued is a problem with that sort of study is when you present a word at objective threshold, what you're presenting is a highly degraded stimulus that the person can barely do anything with. When you present something consciously, you're presenting a highly visible, good quality stimulus. So what differs is not just the person's conscious experience, but also just the representation, or the visual representation, or the processing itself. So what you have is a really degraded representation and a really good one. The good one happens to be conscious and the degraded one unconscious. But we have a confound now. How good the first order representation is, and whether it's conscious or not. So what we really want to do is to have a first order representation that's exactly the same degree of goodness, and have one conscious and the other unconscious. Then we no longer have that confound. You see, maybe the conscious word was highly represented in the brain all over just because it was a good quality representation. It wasn't to do with being conscious, it was to do with being a good quality representation. So Huckman came up with a particularly clever way of equating the first order representation, or first order performance, while changing the amount of conscious experience, or the proportion of times people consciously saw the stimulus. And he did that with meta-contrast masking, which I mentioned before. So remember, with a meta-contrast mask you have a stimulus, and here it's a diamond or a square, and then the mask is something that goes around. It doesn't actually go on top, like backmasking. The mask, in effect, spatially replaces the prime stimulus. With a meta-contrast mask, it goes around. That sounds like a funny sort of distinction, but I don't understand the visual physiology. But it makes a difference to how the mask works, and gives it some unusual properties. So here, a diamond or a square is presented. It's masked. The person has to say whether it was a diamond or a square. Now, in saying whether it was a diamond or a square, is that a first order or a second order judgment? First, yeah. First order means about the world. In other words, you're just saying, how is the world? It's a diamond, it's a square. So that's a first order judgment. And then the person said whether they in making that judgment, whether they saw what was there or they were just guessing. And so that's a second order judgment, that's right. Because you're saying what your mind is like. What the mental state was that beheld the world. So second order. It's a judgment about the mental state about the world. Now with meta-contrast masking, you see here's the SOA, stimulus onset asynchrony. The thick line here is people's accuracy at the first order judgment. Now you see it has this funny U shape. So we start here 0 SOA. As we increase the SOA, performance actually goes down till, I don't know, 50 milliseconds or so, and then performance gets better again. So this is the peculiar thing about meta-contrast masking. I can't tell you why it's like that, but it's a fine thing that nature arranged it to be so. Because then what we can do is, as you see here, pick 2 points where the accuracy is the same. This point is the same accuracy as this point. So an SOA of 100 is about the same accuracy as an SOA of 33 for the first order judgment. So what we've done is we've found conditions where the first order judgment has the same goodness, accuracy. So we could argue that the first order representation is the same quality. There's no confound here in the quality of the first order representation. Because now look at the second order judgment, and that is also a U shape, but it's shifted a bit. So at the 100 milliseconds, there are more seen responses than at the 33 milliseconds. So in comparing the 100 millisecond SOA with the 33 millisecond SOA, we end up with the same accuracy for the first order judgment, but different proportion of higher order thoughts of seeing. Hands up if that's clear to you. So remember, the problem with the previous experiment was a highly degraded stimulus was compared to a really good stimulus. And the really good stimulus activated a lot of the brain, and the degraded stimulus activated a little bit of the brain. Now, do you think that tells you anything about conscious awareness? Maybe not. Maybe it just tells you that a really good, high-quality representation activates a lot of the brain, and a really degraded representation that barely gets off the ground doesn't do very much. So why should that tell us anything about conscious awareness? Because there's a confound in that sort of experiment between the quality of the first order representation and whether you were having a conscious visual experience of it. So what we would like is an experiment in which we have two conditions where the first order representation is exactly the same quality. And that's what's achieved by Mother Nature creating metacontrast masking with a U-shaped curve like this, which seems inexplicable or at least strange to me. But anyway, there you go. For our benefit, we can pick an SOA here where people are 90% correct to the first order judgment, and here 90% correct to the first order judgment. Two different SOAs miles apart where the first order representation has the same quality, at least by this argument. But people think they saw it more often here than here. So same first order representation, so the argument goes, but different proportion of times you're having higher order thoughts. So this is then, the argument is, the perfect, more controlled experiment for looking at the neural correlates of consciousness. So put your hands up if that makes sense. Great. And now what happens when you fMRI scan and compare those two control conditions, instead of getting large-scale activation of conscious compared to tiny for unconscious, in the comparison a specific area came up, the left mid-dorsolateral prefrontal cortex. Now I have to say, this is all with all the provisos. Just because they didn't get significant activation doesn't mean there wasn't other areas activated. But just in terms of what they picked up, Lau and Passman picked up a particular area, the left mid-dorsolateral prefrontal cortex. So maybe a slightly simplistic argument from this is that that is the area responsible for higher order thoughts, because that's the difference between the two conditions. Call it the hot box. So the part of the brain responsible for conscious experience could be, I want to think, a slightly simplistic interpretation, is a particular part of the brain here, the left mid-dorsolateral prefrontal cortex. Notice there is reporting going on in both these cases, in some sense. At least there's a public sort of button pressing of guessing or seeing. So that in that sense there's not a report confound. Any questions? So we have, I said before, maybe prefrontal areas responsible for consciousness. This would sort of nail it a bit more precisely as, yeah, maybe prefrontal areas are crucially important for conscious awareness. So what would happen if you lesioned prefrontal areas? Now, if it was really as simple as that, a precise area being responsible for conscious awareness, and you lesioned it, you'd probably turn into a philosopher's zombie with no conscious experience, and that isn't quite what happens. So, well, here's a paper that looked at the issue. Patients with prefrontal lesions and matched controls were presented with stimuli. They had to say what they were, and there was a mask with different SOAs to look at the threshold at which they could consciously see what was there. Objective performance is saying what is there, and the subjective visibility is this percentage seen response. Did you see it or did you just guess? Then what they found, so we've got SOA plotted at the bottom here, and patients and controls, frontal patients. The patients see less at a given SOA than the controls. In other words, perhaps because of, and this happens even when you look at, you control objective performance, so you're looking at just the correct responses or just the incorrect responses. It seems it's harder for the patients to bring the material. They need a longer SOA to bring the material in, to develop high order thoughts about the material than matched controls. But it isn't quite that they can't do it. It's just that it's more difficult. So I think one would say that these areas are involved in the construction of accurate higher order thoughts, but it's going to be very difficult to localize a particular area and say that is absolutely the whole box that does all the work. Nonetheless, if there's an area like mid-dorsolateral prefrontal cortex that plays a key role in that, that is information we're going to make use of later in the module for understanding conscious versus unconscious processing. Any questions? Now finally, I want to argue that maybe in our search for unconscious perception and subliminal perception, we've been looking in slightly the wrong place in order to see the most powerful, obvious and pervasive examples of subliminal perception. Maybe subliminal perception has been right before us more than we think, namely in perceptual-motor skills. So I want to turn to an example of that and show you how subliminal perception could operate in that case. The question I'll start with is how do you catch a ball? So you're standing, in this case maybe 40 meters away or something, and from someone, and a ball comes towards you, maybe directly towards you, and it's either going to fall in front of you, fall between your eyes, or it's going to go over your head. So you have to decide whether you're going to run forwards or backwards in order to catch the ball. Now people can do this in about half a second, a couple of seconds flying. They'll have launched forwards or backwards and then picked up speed to get them at just the right place at the right time to catch the ball. So you can show you that's what people do. You know people. In some sense you know that, but you can video people and show the timing of how people do this. So how do you manage to do that? Actually, why don't you just think about that now and tell the person next to you, when you introspect on your own experiences, how could a person decide whether to run forwards or backwards, get the right speed to catch a ball, and all you see is blob coming in the right towards you. It might go over your head, it might fall in front of you, it might. Okay, so let me tell you the answer is quite simple, in a sense. Right. A few people just sort of guess it. The key to it is to think about this angle of gaze. So here's the ball coming, the person's looking at it, and his direction of gaze there makes a certain angle with the horizontal. Now, there's only two ways to miss the ball. it falls in front of you, and then what happens to that angle? It goes to 0. The only other way of missing it goes over your head, the angle goes to 90. So there's only two ways of missing the ball. Angle goes to 0, angle goes to 90. If there's any angle in between that, it hits you between the eyes. So your job is to keep the angle between 0 and 90. As long as you do that, it's going to come here and catch you. So looked in that way, you don't need to solve any laws of physics. You don't need to work out a parabola and space and calculate your velocity. You've got one job, to keep the angle between 0 and 90. As long as you do that, you catch it. In terms of being in the right place at the right time. And one thing you could do, and the first thing you might say is, why don't you keep a constant angle? So as the ball comes, I'll just run and keep that angle constant. That would guarantee interception, because if you keep a constant angle, whatever that angle is when you happen to look at it, it will be between 0 and 90, you'll catch it. But if you look at this, you can see it's inefficient. Sometimes you're going to have to run backwards, away from the right place, turn around and hair forward at top speed. You will catch it, but it's a bit inefficient. So what's better is to let the angle rise, but do it in a controlled way. It's more efficient. That's what people do. Now they do something rather precise, we found out. Don't even remember about tangents. The only thing I want you to remember about tangents is as the angle goes to 90, the tangent goes to infinity. What that means is if you kept the tangent increasing constantly, constant rate, the angle will never reach 90. It will rise, but it will never reach 90. That means you can allow the angle to rise in a controlled way. It will never reach 90. You'll be in the right place at the right time. And indeed, when we videoed people, top cricket players as well as undergraduates, they all did the same thing. They had these beautiful straight lines of tangent against time. And that's what you do. As far as we know, that's what everyone does. You keep the angle increasing in this very precise way, in a controlled way, so it will never reach 90. You don't have to solve, even unconsciously, a single differential equation, no parabola. You don't have to know anything about a lot about the world and what's going on, as it were. All you do is you adjust your speed, accelerate, so that tangent is increasing linearly. You're just monitoring this angle here, this angle of gaze, the tangent of that angle. So there's a perceptual variable here, the angle of gaze or the tangent of the angle of gaze, that you're controlling very precisely. I wonder if any of you in your discussions just now, did you say, oh, the tangent of the angle, you know, I keep that very precise when I run to catch that ball? So this seemed to us to be a good case of unconscious perception. So there's this perceptual variable here you don't probably even know exists. You didn't probably even have a name for it before, that you're controlling very precisely every time you intercept something, quite automatically. But it seemed unlikely you'd be aware of that perceptual variable, that you'd had higher order thoughts about it in any relevant sense. Of course, we can't just say it's unlikely when you do an experiment. So Nick Reed, a PhD student, looked at this a bit more closely. Do people know consciously how to catch a ball? So one thing you can ask people to do is to say, how do you go about catching a ball? You can describe the angle of gaze to people and say, how do you use that? How will that change? when you ask people to do this, the most common response, they say, is the angle of gaze increases to halfway through the flight and then decreases for the rest of the flight. If you ask them, you define the angle of gaze for them, this perceptual variable, and ask them to think about what happens to them when they catch a ball, they say, well, it goes up halfway through the flight and then it comes down again. Now, presumably what they're doing is they're imagining a parabola sideways on, the flight of the ball sideways on, so it goes up. Because you're not sideways on, the ball is coming towards you. And what actually happens to your angle of gaze is it goes continuously up. Continuously up until you catch it. In those graphs before. In fact, if they followed this response of allowing the angle of gaze to go down from halfway through the flight, not that they'd ever know when halfway through the flight was, it would guarantee failure of interception. So people consciously describe a strategy which would ensure their failure if they enacted it. One thing we did was to define angle of gaze, get people to say what they thought would happen to angle of gaze if they caught it short, caught it high. People are quite good at that. If you sort of catch it short, you know it's going to come down at some point. Catch it high, you know it's going to come up at some point. But if you ask them what happens when you catch it at eye level, this is mean accuracy, they tend to get that really wrong. They don't know the angle of gaze just increases until you catch it. So at the crucial defining condition of what it is to intercept a ball that defines all other conditions, that's precisely where people get it wrong. In fact, they still get it wrong even if you ask them to run and catch a ball. Notice their angle of gaze as closely as they can, and immediately afterwards we ask them what was happening to their angle of gaze. They still can't quite grasp what was happening to their angle of gaze. When we ask for confidence in these different responses, you see they're equally confident in all of these things. In other words, they're highly confident in their completely incorrect answers about what happens in the defining condition of intercepting a ball. So people use an incorrect theory when giving a choice of descriptions. They sort of imagine the flight of the ball sideways on. A theory that if they implemented their own suggestions wouldn't work. They would fail to catch balls. They seem unable to even get the right answer when you ask them to introspect on the angle of gaze and take a catch, and immediately afterwards give forced choice descriptions of what was happening. And they're very confident in the wrong theories. So here's an unusual case where the unconscious knowledge is better than the conscious knowledge. And I think in this particular case it was because it was sort of evolutionarily hardwired. And it was probably hardwired not in order to catch cricket balls, but sort of the opposite, to avoid being hit by things. So if you're standing here and something's coming towards you and you have to know whether to get out of the way or not, it's the same principle, right? You know whether to get out of the way or not. Now, then when you learn to catch things, you just run that in reverse. You say, okay, I'll now reinstate the experiences I have when I get hit by things, and that will mean I intercept objects. And the solution, the evolutionary solution to this is so simple in a way in terms of controlling angle of gaze. I think it was set up to be protected from our flexible general conscious knowledge. Evolution didn't want our conscious knowledge to be able to control this particular mechanism precisely because conscious knowledge is so flexible, so good at coming up with all sorts of different solutions. It could have come up with any old stuff. There is one solution that works well, so let's just stick with this and shield it from good old flexible general conscious knowledge. So maybe when there is a clear, simple solution to an ecologically important problem, it's safer to keep performance shielded from conscious knowledge. Now I suspect that, although we've looked at it in this particular case, that in terms of perceptual-motor skills, that the principle is more general, that there's a lot of perceptual variables we use that don't figure in our conscious experience. They're not sort of amenable to higher order thoughts very readily. And that probably is the domain of subliminal perception that's with us all the time. Sort of not backmasking and that sort of thing, which is sort of the cognitive psychologists' little artificial procedure. So to summarise, people can see without being aware of seeing, as shown by especially subjective thresholds, and for me that's the clearest and most theoretically motivated case that makes sense and is interesting. But also objective thresholds to a certain extent. You can degrade a stimulus so sometimes it's barely seen at all because the person can't even discriminate what was there, so it's sort of debatable even the perception, fully fledged perception, what's happening per se, but there's at least information in the brain often that will influence further processing. That happens at the objective threshold. And this knowledge can allow specific activities, so this is what we've talked about. Catching a ball, guiding attention, that was with the naked bodies, biasing preferences, emotional stimuli can make you find other things more pleasant or less pleasant, and very limited degrees of strategic control. So to finish with, why don't you consider one of those examples there that you found most interesting and describe it to the person next to you.